start recording this. Oops. Okay. So we're going to start off, and I think we can all agree that the average acceleration is equal to delta x over delta t. Yeah? Okay. I'm sorry. I said acceleration. I wrote velocity. The average velocity is equal to delta x over delta t, and we all agree on that. That's on your note card. Now, here's the other thing. You all know how to find an average of any two values. So, also, V average is equal to VI plus VF divided by 2, because that's how you find an average for anything, correct? Good. Well, we can actually set those equal to one another. What this is starting to get us towards is one of those factors in a situation where the velocity is changing and there is acceleration, but we don't know what the rate of acceleration is. We don't have the rate of acceleration, but we have an initial and final velocity. These are really useful, especially when we've got coming to rest and starting from rest problems, where one of those is 0. But we can use it any time we know initial and final velocity, or when we want to know initial and final velocity, as long as the rate of acceleration is constant. So the common form that we use for this, we rearrange to solve for delta x. And we're going to pull out that 1/2. And I'm actually going to scoot that down. Looks better that way. So what we get is delta x equals 1/2 delta t times the quantity VI plus VF. So if we've got any problem where we're trying to connect the displacement, the time interval, and the initial and final velocity, this is your creature. So that's what I have right now. We're going to go ahead and we're going to do sample problem 4C, and then I'm going to turn you loose to do 4C. Good Lord, no, that would blow your minds. 2C, and then I'm going to give you some time to work on the 2C book problems before we do our next derivation. Okay, so we're given a race car, reaches a speed of 42 meters per second, then begins negative uniform negative acceleration using its parachute and braking system, and comes to rest 5 seconds later. Find how far the car moves while stopping. Yes, sir. So I realized that I modeled a little bit of a bad habit. When we only had those two equations, and we always knew which one we were going to use, because if there was any acceleration, we were going to use A equals delta V over delta T. I didn't model the habit of write down your variables first. That's really important, because we're going to get to a point where you've got 6 equations to pick from, and you need to know which one you need to pick. And the only way to determine which equation you need is to know which variables you're connecting. So what is our VI? 42 meters per second, pretty zippy. What is our VF? 0. We want delta x, that's our unknown, and we're told that delta t is 5.5 seconds. This is a classic stopping distance problem, and you can do this for your own vehicle moving down the highway. How, if your car is capable of, well, actually, no, this isn't even rate of acceleration. What is your stopping distance, or what is your stopping time? How long will it take you to stop? So we've got VI, VF, delta x, delta t. That means we want to use this. And we don't even have to rearrange on this. It's pretty straightforward. So delta x, we get 115.5 meters. Oh, let's do the dimensional analysis check here. So meters per second plus meters per second equals meters per second. Seconds times meters per second gives us just meters. Sig figs, we have 2. So this is 120 meters. all of the 4C problems are assigned. So I'm going to have you go ahead and start on that. And then we'll come back momentarily and look at a few thornier ones. With the airplane problem, the conversation I want to have is about problem solving, substitutions, and multi-step calculations. So we are given VI, VF, a rate of acceleration, and it sure looks like, well, we're given a distance, we're also given a time, but, or no, we're not given time, I'm sorry. There's no mention of time in the problem whatsoever. There, get rid of that, go away, go away. VI is what, 100 meters per second, VF is stopped. The acceleration is negative 5.5? 5.5 meters per second squared. And delta x, well, you know, do we... Oh, 5.0. Okay, thank you. 5.5 was from the last problem. I'm getting them all mixed up. Do we know delta x? Well, that's a great question. We're given the length of the runway. Do we plug that value in? Do we not plug that value in? So what a few people have objected to is, not really objected, but, well, you know, the equation that we just learned is this. So by God, I better use time. But we don't have time in this problem. The thing about your note card is once we have an equation, it's fair game. Which means instead of looking at it in terms of, you know, this is the equation we have, these are the three equations we have, so we may be using any of them. And you know, so you can cleverly, the reason to list your variables is you're looking for which equation connects the things that you have. Well, in essence, you have the change in acceleration, you have acceleration average, there's nothing about time, yet we have an equation that would connect change in velocity with acceleration and time. You have delta x, vi, vf, but you don't have time. I'm starting to see something emerge here. So one thing you can do is solve for time using the acceleration equation. And a few people did that as a first step. And then you can plug that value for time back into here. And that's legal. Here's what I'm going to tell you. It is legal. You can do that. I'm going to say this once or twice or 3.5 million more times this year. There are 6 ways to solve any physics problem. 4 of them will get you an answer. 2 or 3 of them will get you the right answer. 1 or 2 of them, usually one of them, is elegant. So elegant mathematical solutions. And for some of you who are thinking about computer science stuff, I hear my husband complain about this at the dinner table all the time. When you're coding something, elegant coding is the straightest, simplest path through a problem. And in physics, the most elegant solution is the straightest, most simple path through a problem. Often with the fewest number of solve something, plug it in, solve something, plug it in, solve something, plug it in, which means we tend to rely on substitutions. So you can solve for time and plug it in, and it's legal, but it's clunky and it's kind of juvenile, really. The other thing you can do is this. So we've got that, and we know that that's also then equal to, well, we'll just leave it at that for right now. We can solve that for delta t. Well, now what we have is an expression that can go in there. It's a substitution. So I'm going to go ahead and do that. This gets you an elegant solution. This gets you a single equation into which, does this connect the factors that you're given? Yes. The thing that connects the factors you're given while incorporating nothing that you weren't given is generally your most elegant solution. My first 3 years teaching physics, I used to give a bonus point on tests. If you found a more elegant solution than mine, you got a bonus point. And I haven't had to do that in a long time, but I will not say it's not possible. So I encourage the most elegant solution possible. This is also why we do things like mistake game. So when Vince came up and he and I were thinking through it together, and I actually had a mistake in there that was a pretty good mistake, if I was playing the mistake game with myself. So when you're doing more of the algebra, you have to be able to trace through and find errors. Does that make sense? That said, am I going to mark it wrong if you solve for time and plug it in? No, I am not. So you want to check this and make sure this one works? Because I haven't checked it. Does it work? Did I screw something up? Actually, I'm gonna shut up. I'm gonna stop this recording. We'll do a separate recording for our next derivation in a little bit.